Alright, class, this is the screencast for week 7, and our main topic is territories in movement, least cost path analysis in particular, which I'll get to here in a second. But before we get to that, I thought I would start just with a quick example of the best practices for organizing your data that I talked about on Tuesday. So I'll just show you how I have my data organized for the class data, but I have all of my data for all my research projects organized in a very similar way, both on my external hard drives and on my other computers. So we'll just go here. It's called Home on Linux. This is just sort of the base directory for data in general. There's a bunch of folders here. I chose Documents for where I'm going to keep everything. Okay, so for me, the base path is Home IULA Documents. And then it's called Class GIS Data. Now, for my research purposes, I would just call this GIS Data. I put the little class in front of this because I'm keeping the stuff I'm doing for this class separate from my research work. But I would have GIS Data right here. This is the base directory below which all of my GIS data is going to live. If I needed to back up, for example, all of my GIS data, I could drag this over to, or copy this over to an external drive, and it would back up all my GIS data because I have it organized within this folder. So if I open this folder, you see it contains 3 separate directories or folders underneath this. One says QGIS_projects, one says GRASS_database, and one says exported maps and graphics. So I'll take these one at a time. I'll start with the GRASS database because this is probably the simplest, because GRASS is so explicit about the way it needs its data organized. In fact, it does it for you, and it won't even start up if the data isn't organized the proper way. So when you start GRASS up, this is the directory that you actually pointed to. This is your GIS database, your GRASS database. All your GRASS data lives below this folder. All right, so if we open this up, you'll actually see physically these are GRASS locations, all set up from within GRASS, but they are literally just folders on my computer. If I open up any one of these, you'll see at least one map set called permanent inside that. And if you open that up, you'll have a bunch of weird looking files and folders. These are the actual data for the different GIS files, the raster and vector files. Now they're all broken up and organized in a very special way. You should never move anything around inside this folder, especially if you don't really know what you're doing. All right, let GRASS deal with this part. However, if you have 2 locations that are similar, you could certainly move map sets physically, copying and pasting them between them if they're in the same exact projection system, and only if they're in the same projection system. Again, if you don't really know what you're doing, just leave it alone, but this is a relatively safe space for moving folders around different map sets. If I had one that has more than one map set, for example, I could move this over to a thumb drive and then onto another computer that also has a North Carolina Basic GRASS 7 location in there. It would be fine. These locations you can also move around. They have to be within one GRASS database or a GRASS database on a computer to get them, but you can certainly copy them individually, and as long as you put them in another folder that's your GRASS database folder on whatever computer you're using, that will be fine. All right. In general, it's just easy. You could grab just your whole GRASS database and back that up. So it's very hierarchically organized. It's the file tree for GRASS. QGIS has no such requirements, meaning you could have your data theoretically anywhere on your computer, and as long as you remembered the path, the actual path down through all the file folders to get to each file, QGIS will open those folders and those files, I mean. Now, this presents a problem for you because it's very easy to get disorganized. So I suggest you follow something fairly similar to the GRASS hierarchical model for organizing your QGIS data. The only difference is that you have to do this yourself on purpose by creating the folders on your computer. So I open my QGIS projects folder. You see I just happen to have 2 projects in here. The sample data, QGIS sample data that we downloaded from the QGIS website, and Lemon Grove Tree Survey, which is Project 1 that we completed recently. I could have called this Project 1. I tend to like to give these project folders very descriptive names because 3 or 4 months from now, I may have no idea what project 1 actually was. So I'll remember what Lemon Grove Tree Survey is, so that's why I call it this. If I open this particular project file, this is what I'm going to call this project folder, you'll see I have 3 things in here. I have a folder called rasters, a folder called vector, and an actual QGIS project file. This is, like I told you in class, literally just saving which layers are currently loaded in the map canvas. The data themselves are in these 2 folders. So if I open the vector one, you'll see I have several folders within that. Each one has a name: cultural resources, historic buildings, city limits, parks, soils. Each one of these folders contains a shapefile, which is actually multiple files. You can see DBF, PRJ, SHP, SHX, SBX, SBN, this XML. All of these things are part of the shapefile. They need to be together for QGIS to be able to load the shapefile. So you don't want them to be separated, which is why you should stick them in their own folder, right? Each one of these things is like that. Its own folder for one shapefile, because otherwise it's really easy to get messed up, all right? Under the raster, I have basically 2 SRTM DEMs that we downloaded from the USGS Earth Explorer data portal. They come as a TIFF, and then they have this XML, which is the metadata, right? And because there's really only these 2 TIFFs are the only things that are important, I just keep them directly within this folder. And this, like I said, is literally just a piece of information for QGIS that says where to look in the computer for the layers that you had loaded when you last saved this QGIS project. So if I double click on it, it'll open QGIS. It'll then think about it for a second, trying to find all those layers, and then it finds. In this case, I happen to have the tree survey grid and one of those SRTM DEMs loaded in. And as long as you keep your data organized in this way, where you have the project file right in the project folder, and then your actual data in these directories below that, you can move this folder, this project folder, around, put it on thumb drives, zip it up, and send it by email. And then whatever computer you use, if you double click on this, it will open up exactly the layers, right? Because it only cares about what's below it in the file tree, not about what's above it. Okay, so that's the best practices for organizing your GIS data. Oh, I forgot one last thing. I have way back up here, right under my GIS data folder, I also have exported maps and graphics. This is not necessary, but I tend to like to do this. So if I export images from GRASS or from QGIS like these, it's just nice to kind of keep them somewhere. You could export these kind of things directly, for example, into your QGIS project folder. You could even have a third folder here that says exported map products for this project. Either way, you just want to have a nice place where you're going to tell it to export the maps and graphics so that you can find them. So you don't just randomly have them exported somewhere on your computer and you have to then go clicking through all of your folders to try and find where the map you exported was. All right. The key to all of this is just to stay consistent. Come up with a system. I suggest this particular system. You can modify it so that it works for you, for your workflow. But you should come up with one system and you should stick with it, and you shouldn't make changes, because changes to the system are what cause problems. Broken project files, missing data files, accidentally deleted data files, all of that kind of thing. Okay, so now that that's all been said, what I'm going to do is start up GRASS, and we will talk about least cost path analysis. So you got to point your GRASS database to exactly what I was talking about. So this is my class GIS data in my documents, and here's my GRASS database. Just highlight it, don't double click on it, right? Click open. That's the path starting from the root of my computer all the way up to this thing. Then it finds all of the locations and then all of the map sets within each location. So we're working with the Wadi Hassa data set again. Wadi Hassa UTM zone. I have written 32 north, and that is a mistake. It should be 36 north. I work in also northern Italy, which is zone 32, and this is a reason why you have to always be very, very careful and double check the things that you write. So at one point I should go in there. In fact, I'll do it right now. I will quit out of grass. I'll literally go in here, find this folder. This is the grass location, but I can actually rename it here. I can just hit rename in my little thing, and I can change that to 36 north, hit rename, and then when I start up grass, it's going to go back. It's going to find, well, I got to find class GIS data, grass database, open, and now you see it's actually just reading the name of that folder, and everything else is fine. So I just fixed my mistake. So never work in permanent after the first time. You only want to import your base data in permanent, and you want to work in a separate map set. All right, so project 2, I'm going to keep working in that same map set that we were working in last time. Okay, so grass is now loaded, and what we can do is just load up our base files. We can load the DEM directly, but let's just load up the hillshade that we made last time. I have it right here. 30 meter hillshade times 3, let's say. That's the one we made in class, right? So that's literally just the hillshade file showing us some of the elevations. Let's stick some of the sites on it. I'll just pick the WHS sites for now. Okay, so this is basically more or less what we were looking at last time. This is essentially where we got to. We did do the hydrologic analysis. I'm going to go back over the hydrological analysis here in a minute because we went through it rather quickly. But before I do that, let's just talk about doing a real basic cost surface analysis. Least cost analysis sometimes, accumulated cost analysis. In general, there's a variety of ways to talk about these things, but basically what we're trying to do is figure out something to do with movement across this topography that we're seeing very vividly here in the hillshade. All right, so let's start with the simplest case. We'll start somewhere in the middle. I will randomly query a point just here, and I'm going to move this query results off to the side. One of the things that you do when you just pick the query tool, this one over here, and you click somewhere on the map, it actually gives you the coordinates here, the east and the north. And if you right click on it, you can actually copy the coordinates themselves to the clipboard. So that's a really useful thing if you just ever want to find out the X and Y coordinates of any place. You can use the query tool, and then you can copy that to the clipboard. So I've just done this. This is going to be our starting point for our cost surface analysis. Now the first thing we need is to figure out what they call friction, or the friction surface. And all this is really some cost for traversing a grid cell. Remember, if we zoom way in on our raster map, we see these pixels, right? Each pixel in the raster map is a certain resolution. In this case, they're 30 meters. That's the resolution of our base DEM. So we want to know some sort of cost associated if I was to walk across this pixel in any direction, all right? The routine may or may not need to know that walking across it in a diagonal is actually longer. We are just going to say a base cost. Traversing this cell in any way, if you go across it, it's going to incur some sort of cost. So let me just zoom back to where we were. And let's talk about the kind of costs that we could potentially use. Well, there's a lot of things. Is there vegetation there? That might make it hard to move across. Is it steep? The steeper it is, the harder it ought to be to move across, right? Is there some sort of cultural cost or social cost for moving across that cell? Is it in the territory of an enemy? Is it water? Is it land, right? Is it rough and rocky? Is it smooth? There's a lot of things that we could potentially put into this friction surface that we could use as the base of our cost analysis. For now, we'll pick one of the easiest things and something that we've already calculated last time, which is the topographic slope in degrees for this entire area. So I'm just going to load that map which we made last time. We called it slope, which was good. And it looks like this. This is with the colors that we styled from it last time. All right. So all the pink and red areas are steep slope, and all the yellow areas are low slope. Let me just put the legend on real quick and click OK, and I'll just drag it over here. So there we see, right? Steep slope to low slope, right? That makes sense because the steeper the landscape, the harder it is to actually walk across it. So let's use this as our friction. It's pretty simple, it's straightforward, it's not the most robust method, and we'll see there's a couple issues with the output, but for now it's a really good base to choose for our starting point, which we clicked, which was somewhere around here. All right. So let's go to our raster menu, and we'll go down to terrain analysis, and we'll find the one that says cost surface, r.cost. So we open that up. And basically what we have here is the first tab, required, name of input raster map containing grid cell cost information. And because I already had slope selected in the map layer, it loaded that in automatically. That's great. That's what we're going to use for our cost. The output map, I'm going to just put slope costs 1, right? Just because we're starting from 1 point. There are a couple other things that we could do here in the optional outputs. We don't necessarily need them for now. Again, everything has a really good manual page, so you can read about all the different options and the way these things work here. All right. Let me actually just expand this so you can see. So here's the manual page. All kinds of information about the cost surface routine and the different options that you can choose. What we really need is a starting point to start from. We could choose a vector points map to start from, and this could be one single site, or it could be a whole bunch of points, and it would simultaneously start walking from all of them. To keep things simple, I'm just going to, with a copy and a paste from before, so remember I had my my query results, and I copied them out of here, right? That's all I did. Copy, and I got rcost, and I just hit paste, which is Control V. Whoops, I should not have done that twice. Back it up here. Paste, boom, in there, right? So this is our X and our Y of our starting points. Again, I could have had a starting vector points. In fact, I could have little points in raster format. We may talk about that at some point. It's useful for certain things. In general, you'll either have a vector points map, or you'll have a coordinate that you want to stop from. You could potentially tell it to stop when it gets to a specific set of points. We're going to ignore that for now, and we're actually going to ignore everything else for right now. We could potentially check this box if we wanted a slightly more accurate cost surface. It takes a little longer to calculate, not that much longer, but for now I'm just going to keep things simple. Exactly the slope map, the output map, and a set of starting points. And I'm just going to minimize that and hit run. So we'll see it's doing it, finding its way from that start point across all cells in all directions. This can take a while, right, depending. In this case, it was actually relatively quickly, right? So remember, our starting location is somewhere right here, and we actually see the color. So let me just update the scale. We'll find our slope costs 1, and actually I should change now the font to be white so we can actually read the numbers. There we go. All right. So black is low cost and yellow is high cost. We can change the colors with color rules like I showed before if we wanted to. In this case, it's fine for now. We'll just leave it because, you know, this color scheme is actually pretty easy to see how the patterning of cost. And we can basically see that there is some higher cost areas to walk through and some lower cost areas to walk through. So basically walking through the valley out to the Dead Sea area. This is basically the most efficient route to that area from where we started. All right? Now, you may be asking yourselves, what do these numbers over here actually mean? What is 9925? What units are that? Is that the time it takes? Is that the difficulty, the energy? Actually, what it is the accumulated amount of whatever it is you stuck in the friction surface, the cost of traversing a cell. Remember, we used slope in degrees, so literally this is the accumulated amount of slope angle that you've walked as you went through all of the cells. What does that actually mean in reality? It means actually nothing, all right? This is a essentially unitless or non-meaningful cost surface output. The patterning is correct, right? This is the lowest cost way to go across this slope in the direction that we're walking. But the numbers in there don't tell us anything. We cannot derive, for example, the amount of time it would take to walk from our point here to any other point on the landscape. We can basically just say it's easier to go anywhere that's darker and harder to go anywhere that's lighter. All right? So what do we do if we actually want to use or to find out, for example, the time to get from point A to point B walking along the easiest path? Well, we could use one of the formulas that we learned in the paper by Devin White in Advances in Archaeological Practice, the 2017 paper. We could calculate Tobler's hiking function according to his directions, and we could use the output of that into the input here for our R cost, where it says containing grid cell cost information. Well, that would require using the map calculator, which we haven't used and which I'm not going to teach you just yet. So in this case, let's not do Tobler's hiking function, but let's instead use a different module built into GRASS that does some of the math for us. All right, so we'll go back to our raster menu, terrain analysis, and we'll go down, instead of the one that says cost surface, we'll go down below it, cumulative movement costs, r dot walk. So we'll click on that, and we have something similar in the required tab, except it's asking now for an elevation raster map, a map containing friction costs, and then an output map. So this particular module, before I even get started, I'll just come down here to the manual, and I'll expand it. Come here. There we go. Okay. It's going to apply this formula right here. So it's going to calculate slope from, on its own, from the DEM that you put in. It's going to calculate a variety of other things. And basically what it's doing is applying a formula to figure out, based on the average speed of a human being on flat land, going downhill and going uphill, what's the walking time to traverse across the landscape, across all the cells. So you can read through this if you want to know more of the details. Here's the function right here. But basically that's what you have to do, is keep that in mind. This is actually going to come out in seconds of walking time, and it's going to matter whether you're walking uphill over flatland or downhill from where you start. So it's going to produce very different results from even the patterning of the basic cost surface that we did before, because it's going to be different for going uphill versus going downhill, whereas before it didn't matter. It was just what's the slope in general. Okay? So let's talk about the inputs. The elevation map, you have to pick your DEM, Hasa 30 meter SRTM. What is this? What is the friction cost? Well, isn't it calculating all of that inside? Yeah, but you have the opportunity to actually add additional friction costs. So if you have some additional information in addition to just walking over different slopes, uphill or downhill, whether the terrain's rough or there's vegetation or it's wet or whatever, you could make a map with additional number of seconds per cell and input it. What we want to do in this case is not have this really affect the routine. In order to do that, we have to make a map, a very, very simple map with just the number 1 in everything. And the simplest way to do this is to fast forward to the map calculator, which is under raster map calculator, r.mapcal. Now we're going to have a whole lesson on what the heck all of this stuff is. But for now, just follow my instructions. Enter the number 1 and put friction in the name for output map to create and hit run. And literally what we have done is made a map where every single cell is the number 1. All right. All this does is say to our walk that the friction surface, which is required, you can't run it without putting one in there, is going to be the same for every single slope or every single cell in here. And it's not really going to change the way that the routine works. Okay, and now we'll put walking costs. Okay, that's going to be the output name. Again, we could start at different points, raster or vector points, or we could start with our coordinate that we queried from before. We could stop at a certain place, and there's a few other things that we can tweak. This is the values of certain parameters in the walking costs formula. Leave these alone. These are set for the default walking human walking rate. So for now, just leave these things alone. So we'll hit run. This will take maybe a little longer than the other arc cost, but not that long, right? And there we go. Ah, interesting. We have a very different output from before. Okay, so I'll just be going back and forth. This is our slope costs map, right? We have one pattern, and here we have walking costs, taking into account going up and downhill. We can actually see a very different pattern, more radial, but still along the bottom of the valley here is probably the easiest way. But you can see there's a lot of difference between the two outputs. This particular one, let's change this to be from the slope costs to walking costs. There we are. Okay, so now we actually have numbers. These are actually seconds. Seconds of walking time. This is a much more meaningful unit for us. And if we wanted to convert this to minutes or hours, we can do that, divide by 60 and divide by 60 again, right? Pretty simple to figure out the time it would take for you to walk from here to the Dead Sea. Let's see how much, 84,053. I'll just pull up a little calculator tool. It's just a simple little calculator tool. So I'll put 84,053 and I'll divide by 60, right? So that's 1,400 minutes, divided by 60 again, or 23.34 hours. So it would take roughly a full 24 hours to walk from our starting location up to the Dead Sea or out to this part, right? That's really interesting and good information to know, very applicable for many archaeological problems. Again, we can make this more realistic by adding additional friction costs. Those could be physical costs, and they could also be social costs for territories and that kind of thing. Cool. So that's a basic least cost analysis with walking costs and with other just more esoteric costs like slope or something like that. Let me remove these layers and talk about one particular aspect that we may want to use a cost surface approach for. We might want to know what is the minimum walking time from a set of sites to, let's say, the nearest stream, right? So the first thing we need to do is actually make a map of the streams, and we're going to use the hydrological analysis that we did last time to do that. I'm going to go back through that now because, again, we were rushed last time. So to do that, we go to the raster menu, hydrologic modeling, and we pick our watershed. There are a variety of tools that will let us do something similar. I personally like our watershed for most landscapes, for most scales of landscapes that we're going to be working in. All right. All we need to do is to tell it the name of our DEM, HASA 30-meter SRTM. These other things are important for other kinds of outputs from our watershed, but in this case, we're really only going to output the flow accumulation map, flow ACC, and that's really all we need. We can we can make a bunch of different outputs over here, but this is really all we need for the particular analysis that we're going to do here. On the optional tab, I tend to like to click this use positive flow accumulation for likely underestimates. This is a feature that is supposed to be useful to be able to differentiate from places where water is flowing off the edge or maybe coming in from off the edge. In practice, it just is confusing. So I almost always check this box when I do flow accumulation over here. I often also hit beautify flat areas. It just makes it a little bit more realistic in really flat parts of the grid, right? Also, I believe I probably already have a flow ACC already done, so I'm just going to overwrite it. We'll hit run. You'll just see again how quickly it is on my relatively slow little laptop here. And there we go. That's our flow accumulation value over here. If we change our scale to be flow ACC, we can see very, very large numbers, and we can barely see any of this yellow stuff at the bottom here. But essentially, the darker the color, the larger the number, the further down the drainage it is. So the yellows are ridges, the greens are sort of upper catchments or slopes, and then the blues and the blacks are your channels. So we're going to want to extract some of those channels. It's pretty simple to see how the GIS could figure out where the channels are from this information. In order to do that, we're going to go back to our raster hydrologic modeling, and we'll pick r.stream.extract. And it's going to ask you for the name of your input elevation again, Hasa 30 meters. We'll come back to this in a second. It's going to also want to know your flow accumulation map, flow ACC, and the name of your output map. In this case, you can do it as a raster map or a vector map with streams. We'll pick vector map, right? Streams, right here. Okay. Go back to the initial required tab, minimum flow accumulation for streams. So basically, that's the minimum in this number of flow accumulation value for when we're going to say this is no longer just flowing water across the landscape. It's in a channel now, and it's a stream. This is where you, as the scientist, have to take the reins, because if you're interested in little tiny streams, little gullies, you're going to want to put a relatively small number in that slot here. If you're only interested in the big trunk streams, you're going to want a relatively big number in the trunk streams over here. Whoa, what happened? Okay, we're gonna restart grass for a second here. Something ran out of memory on my machine here, so we're just gonna exit out of grass like that and start it up. See, it happens to the best of us, right? This is the problem of using a relatively low-powered laptop. So we're just going right back into where we were, okay? Boom, back to grass over here. Let's load up our hillshade right there. Okay, so we'll just leave this here for now, just the hillshade, okay? So, oh yeah, let's also put our flow accumulation just so you can see that. Flow accumulation, we'll put our scale back on. Raster legend. Okay, there we are. Boom, right back where we were. Let's go back and get our hydrologic modeling, our stream extract, pick our elevation map, right, Hasa 30, output map for the vectors is streams, input map, also flow accumulation right here, flow ACC, and required tab. I'm going to put 5,000. You should play around with this and just see what the difference is. Now, if you want to play around with this, you can continually overwrite those maps by checking this allow output files to overwrite other things, right? So we're just going to hit run. It's going to chug through. This takes a little while. It's actually pretty computationally expensive, but relatively fast, relatively optimized for grass. And writing our vector map. There we go. Okay. So you can play around with this, continually changing this value and writing new maps out. I'm satisfied with this. You'll notice this gives me a streams map, but it's also got some points. The points are where the streams initiate. You may be interested just in the points where the streams initiate. In general, what we want to do is just focus on the lines, right? So in everything that we do from here on out, we're going to be kind of focusing on the lines, all right? There are a couple of ways forward from here, but probably the easiest way is, instead of going from sites to the streams, let's go from the streams out to everywhere, and then we'll query at certain site locations, all right? So what we need to do is to generate a series of starting points along the lines of the streams for the least cost path routine to take. You do this a couple of different ways. The absolute simplest way is to convert the vector streams line to a raster file and just use that as the raster starting point. I often do it that way, but I'm going to show you a way that's a little bit more flexible. So in case you don't want points at every single raster cell that intersects with the line, if you want to space your points out a little bit for whatever reason, I'm just going to show you a tool that will let you do that. All right, so we'll go to the vector menu. We'll go down to where it says generate points, and we'll go over to where it says, where is it? Generate points along lines, v.2.points. Okay, so again, I have streams selected over here, so it automatically loads that in the input vector map. So we want that, that's good. Here we'll just have stream start points. That's going to be the name of the point vector file that gets produced. Under the selection tab, we want to make sure we only select line because we want to extract along those lines. And that's basically it. There are a few other things that we could do here, but we don't need to do that. So we'll just hit run for now. It's going to take a little while. It's going to make, whoa, what is that? Actually, all of those are points. So if I zoom in on some segment of the stream, we can actually see, actually what I should do is turn flow accumulation. We see these points, right? In this case, I left the default at 100 spacing. I could have put 30 and it would have picked one per cell, but I just used the default of 100 meters between each point along the stream. All right, let's zoom back out. So now you can kind of see what it is, right? So basically what's going to happen is we're going to run the least cost path routine with rwalk. It's going to start at all of those points. It's going to walk outward and make us a nice cost map in walking time that is walking from every part of the stream, walking out upslope from it. Okay? So back to terrain analysis, r.walk. We're going to pick our input elevation map. Again, that's our HASA 30 meter SRTM. We'll use our same friction map that we made before, which is all ones, so it's not going to affect anything. And here we'll have streams walking seconds. All right, that's what I'm going to call the name of the output cost surface. We'll go down to the start map. This time we'll select starting vector points map. We will select stream starting points, and we will hit run. There it goes. All right, so that looks kind of interesting, kind of neat. Let me update the scale over here to streams walking seconds. Change the font back to white since we have kind of a dark color scheme. There we go. All right. So now we can see all the dark areas. Basically, that's all the courses of all the streams. And then the little routines are walking away from that. Basically, it was forced to walk upslope from the little canyon or the valley or the gully that the stream was in upslope. So the light areas are high cost, long seconds away. And the dark areas are real close to the streams, very quickly to get to from the stream bed. So 10,526 is the maximum distance from any stream that looks like to be in this particular area over here. Again, we can use our little calculator. We can go 10,526 divided by 60 and divide by 60 again. So it literally only takes about 3 hours to walk from a stream to the furthest point from any of the major streams. So that's pretty cool. That's interesting to know. What we really want to know is how far are some of those archaeological sites from their nearest fairly major stream. So let's do that. Let's pick, let's load up one of the site databases. We'll pick Wadihasa sites. Click OK. See them all right there. We could do that for all of them. I, in the project 2, want you to query out a smaller selection of them. There's a variety of ways to query them out. We could go down to feature selection and select by attributes via extract, which I've showed you before. I'll show you another little secret, a little shortcut. And let's do it from within the attribute table of this Wadihasa sites. All right. So what I'm going to do is just pick this site type of village, and I'm going to build a query right here in the table. Right. So select star from WH sites where, and then you pick the column name, site type equals, so it's going to be exactly the same, and I'll just put village, right? That's the code right here. I could have put tower or farm or cave or whatever I wanted to. I'll hit apply, and the secret is it gives me a little preview over here. It highlights all of them in yellow. So now I can get a good sense of how many they are and how they are spread across the landscape. Now, what is really cool is that I can now right-click on this selection over here, and I can say extract selected features. Do not worry, this will not delete them from the original table. We are going to make a new vector map that I'm going to call villages. Actually, I'm going to call WHS villages, right? And it's going to keep the attribute data that are already in this. It's going to make a brand new vector file that's totally separate now from Wadihasa's sites. So in fact, it loads it in there, load it up here. And if I make Wadihasa sites invisible, we'll see only the villages. Now these are two separate physical files now, because we ran a routine to extract them into a new vector file. So I can get rid of this from the menu over here, just remove it so I don't have to look at it. And all I'm left here are my sites, my villages, right? And if I wanted to, I could change the symbol to something like squares so that we can see them a little bit better. All right, there we go. All right, now we want to upload the data from this raster map that we're looking at, which is seconds of walking time from the streams, walking away from the streams. We want to upload that data into the table for our WH villages table. Right? So if we open the table, we'll see we have the same columns we had before. How do we do this? Well, we're going to do this with a query, all right, a statistical overlay, all right? And the way we do that is we go down to where it says update attributes, and we have update point attributes, sample raster maps at point locations, vwhat_rast right here, okay? WH villages is the map that we, vector map we want to upload the values to. The raster map we want to query is the one we just made, which we called streams, what do we call it? Streams walking seconds. There we go. Here we can select a couple of things. I often like to check this interpolate values from the nearest 4 cells. They'll smooth out the data a little bit just in case your point happens to be on the border between one or the others. So it'll just give you a slightly nicer or more realistic value for the neighborhood. So I often check that here. And what we need to do is add a name of a new attribute column that we want to add that query to. So we'll put WD, actually what we'll do, I'll call it streams sec. All right, so streams seconds. That's just my little shorthand so I know what's in that column. And that's it. We'll hit run. We'll do real quick. And what we'll do is we'll open the attribute table for that, and we will see that there's now a new column called streams sec. So we have our site numbers over here, our other data that was in the table, and our new column, right? So we can order this from smallest to largest or from largest to smallest. So our largest distance is 3,632 seconds. And what I can do, just again, I can bring up my calculator, 3,632 divided by 60. So that's going to take 60 minutes or about an hour to walk from the stream to the site that's the furthest from the stream. And on the other hand, the closest one is literally right on one of the streams, about 75 seconds away, so a little bit more than a minute's walk from a stream. That's really interesting, right? So there seems to be some patterning here. There seems to be some villages that are far away from streams, and then a bunch of villages that are relatively close to streams. So what do we want to do next? Well, one of the things that we can do is to figure out the linear distance as the crow flies, because remember, this is the least cost path from the village to the stream. So let's do that. Let's use our some of our vector analysis tools, and we'll find the one that says, let's see, where is it again? V distance is what we're looking for. Nearest features is right in front of my face. V dot distance. There we go. Okay. So again, we have from, and we're going to have to. So from is going to be, in this case, we're going to pick our villages as our from, and we're just going to make sure we're going to just pick point, right, like that. And we'll pick minimum distance to nearest features, right? So that's going to be what's going to be upload, and we're going to call this stream lin for linear distance, all right? And then to, we're going to pick our streams map, and we're just going to make sure that we're going to be pointing to the lines, not the points. This is actually quite important right here, okay? All right. So I believe that's what we need to do. It says the column is not found. What we have to do is actually make the column first. Okay, so we'll open up our table editor, and we'll go to Manage Tables tab. We'll add a new column. We'll call it the same name, streams underscore lin, and we'll make it a double. We'll add, and now, oops. Now we basically have a blank streams lin over here. Now when we run it, oh, I called it stream lin, so let me just update what I wrote here. Streams lin. Now we'll run, and it did it. 32 records updated. We hit refresh, and we have values here. So what you have to keep in mind is that this is in seconds of walking time, and this is literally meters, right? So you would have to multiply this by a conversion factor, which I put in the project file. 5 kilometers per hour is about right. So that would be 1,000 meters per hour, right? Sorry, that would be 5,000 meters per hour. And so you basically have to divide. So we'll bring up our little calculator over here, and we would say 625, that's the first value that I'm pulling out from this right here, divided by 5,000 equals 0.125 hours. Okay, so if you want to convert that to seconds, then you have to do some more math to find out the fractions of hours. But basically, you can convert this to minutes or hours or seconds or whatever it is, so that they're both on the same thing. You could do this with a calculator one by one, but honestly, that's a real pain, and we don't want to do that. Instead, what we want to do is export this table and read it into a spreadsheet so that we can do that here. And so what we'll do is we'll go to File, we'll go to Export Database Table, Common Export Formats. We'll pick the table name, which is WHS Villages. We'll browse. Remember our data thing, so we'll go to our class.js data, exported maps and graphics. I'm just going to stick it in there, and I'm going to call it dist to, hey, come back here, dist to streams dot CSV. So CSV is a comma separated value. file. It's a little kind of spreadsheet value. That's what's already here. And I believe we should be able to just hit run. Okay. And if we go back to our exported maps, we have dist to streams.csv. And there we go. That's the table that we were looking at. But now we're in a spreadsheet, and we can do formulas in the spreadsheet. So we can convert very simply a whole column. Streams sec, we can do streams hours right here, and we can put an equal sign. We can put this divided by 60 divided by 60 again, and there we go. I can copy that, and I can select the whole column, and then I can hit paste like that, and it just does all the calculations for me. Now we've got hours of walking time, right? And I can do the same thing with the streams linear distance over here, and I can go streams lin hours, and I can go equal sign this thing divided by 5,000, and now I can copy that and I can paste it down like that. Boom. And now I can compare these things, right? So the linear distance versus the walking time distance. And I can do this one over here. I can call diff. I can enter equal sign, walking time distance minus linear distance. And then I can copy and paste that again all the way down like that. And I've got a bunch of really interesting information now about the difference between the linear as the crow flies time, if I could walk directly straight and topography was no option or no obstacle, versus having to walk down to the stream with the least cost path approach. And we can actually save this. We can just hit File, Save. That's going to save it as a CSV file. If we want our formulas to be preserved, we have to export this to some other kind of format. We can choose, actually, sorry, not export. We want to just do File, Save As. And we can do, if you're using Excel, you just save it as an XLS, XLSX or whatever. For OpenOffice or LibreOffice, which I'm using it, it's ODS, right? And we hit Save. And we can close that, and it's all in there again, right? All of our formulae are in there in all of these things, right? There we go. So basically that's a intro to least cost path analysis in GRASS with a couple of different things that we can do. And yeah, I think that's where I'm going to leave it for now. Next week we will come back with the settlement and location modeling tutorial.